Hi everyone, this is John Wen. So from this video, I will continue to talk about IC-PCP algorithm. From previous video, we were discussing about the algorithms inside IC-PCP as well as the details. And for this video, we will focus on the code implementation in Java on this algorithm. But before we delve into the code, I hope to briefly review what we've been talking about in the previous video. So here is a summary of the IC-PCP algorithm. So firstly, the algorithm is trying to distribute the deadline as a sub-deadlines on each task, and then it identifies a partial critical path, also called a PCP of the workflow, and it assigns each PCP to the cheapest virtual machine, which will satisfy the sub-deadlines of every task in the PCP. It also adjusts EST, EFT, and LFT for tasks on PCP. Furthermore, it adjusts EST and EFT for descendants of PCP and adjusts LFT for ancestors of PCP. So from line 2 to line 6 will be recursively called on the workflow until all the PCPs are assigned. So until then, a plan is done and is ready to be submitted to a workflow executor. So this is a brief idea or brief main idea of IC-PCP algorithm. Let's get into the code. So this code is implemented by Bai and other students, PhD students in our lab. And let's get into the function constructor first. So this is a function constructor, takes two inputs. One is a workflow, one is a location as a string. And this location is basically a JSON file and will be get at the beginning of the code. So you can see this is a example of the JSON configuration file. It contains several things like the workflow name and number of workflow run and execution object. And this object will basically contains all the tasks and their corresponding runtime on different virtual machines. For example, like this extraction task will have different runtime on different virtual machine, like the T2 micro, it has 6.0 time units execution time, and the T2 medium has 4.0 execution time, and also the T2 X large, it has 2.0 execution time. And similarly applied to other tasks, and also has a task transfer object. It contains all the transfer time between the tasks. You can see from the source to different destination tasks and with the transfer time. You can notice that there might be multiple children for one task, so all the children will be specified as destination and the corresponding transfer time will be provided. So this is a configuration file that be read at the beginning of this function constructor, and then we will have a string builder to parse this JSON file line by line, and then we will get the object based on this string and extract the execution object, just as we just discussed this execution object, and put all the tasks and their corresponding runtime on different virtual machines and put them into a hash map called execution temp. And similarly, we will parse the task transfer objects and put the transfer time between each task to a hash map called the edge map temp. And this is the hash map that contains the execution time as well as the edge map as temp. So it also has initialized several things like VM types and VM delay and deadline and time interval, and also the server cost for each type of virtual machine. So the most meat of this algorithm or this code is this plan method. So let's get into this plan method. Basically, firstly, it will initialize, call the init function to initialize the execution or planner. So let's get into what this init method does. So firstly, we'll add processing the workflow. If we go into this edge processing, and we will see that basically at the beginning it will check if the source task, if for every edge in this workflow, and we will check if the source task is none. If it is none, we will add a dummy entry nodes to the graph. So this part of code is basically adding the dummy entry node for the whole graph. And also we will check if the destination task of any edge is none. That means we will add another exit node that is also a dummy node to the graph. And if not, we will go through all the tasks inside and add them into the here is an edge map. Remember, we have edge map temp, so we will get the edges, or we will get the source and the destination task from this edge map temp, and then finally put them into the edge map hash map. So also we will do another thing, because the edge map basically contains the parents and all its child and their transfer time. And also we will need the node parents. That means we will have another hash map that contains all the parents of specific child as a key. So you can see for this edge processing, we get two objects. One is a edge map, and one is a node parents. So let's get back to the code. And next, in the init method, we will get task execution time of the W. So this one will be more straightforward. So I think firstly we loop through all the tasks in the workflow, and we will get the execution time from the task name, and the execution time will be put into this execution time. And keep in mind, basically we encode the key of the tasks by their ID. Like we didn't use a task name because maybe we can have several instances of same task, so that's why we use ID instead of the task name as a key. So this is one thing to mention. Basically this will at the end we'll put the entry node and the exit node to the execution time. And then it will have the entry node as a new task, and also the exit node as a new task. So this is basically the init method will do. Let's go back to the plan method. This is a core meat. And then the next it will do is to build a task time. Let's get into this method. The build task time will basically firstly do the topological sorting of the tasks. So if we take a look at this method, basically we'll check all the tasks from the beginning and find all the child or the children task, and for each child task we will check its parents and make sure the parents is already in the list. If not, we will wait until all the parents have been put before this task in the list, because in topological way we will make sure all the parents appear before the child. So this is one principle we have to make sure, or we have to keep. So after we done this, all the tasks will be sorted in topological way. So let's get back to this method. So then we will loop through all the tasks in the topological order and initialize their task time, and we put the different values like the MET and EST and MFT for the every tasks. And we also will loop through the topological order, and for every task we'll compute or initialize the LFT for different tasks. So this is a workflow planner build task time method does. So let's get back here. After we build the task time for each task, including the EST, EFT, and LFT, and then we will assign the parents from the exit node. So if you remember from the previous video, we start from the exit node, assign the parents for all the parents that are assigned. So let's get into this code. So you can see from here, actually we have a make sure all the parents are assigned. So we have a check here. Then we will do the find PCP of this task. So find PCP is basically to find the recursively find the critical parents. But for me, I noticed that there might be something wrong here in the code, because we only find the max parent once. There is no while loop to recursively find the parents or find the critical path all the way to the entry node. But here only we only find once, and this find max parents is basically just find the maximum or the longest path that from the node to its parents, and just like that. And I believe if we want to strictly to align with the paper, we need a while loop here to find the max parent recursively in order to find the PCP in full. So this is one thing I discovered in this implementation. So after that, we will assign the PCP. After we find the PCP, we'll assign the PCP. So let's get into this method as well. So assign PCP will have, firstly, we will look at the existing instance, existing virtual machine instance. If you look at the paper, it will state very clear. Firstly, to schedule a path on an existing instance, the algorithm considers two cases. So first case is that if the instance executes one of the children of the last task of the path. So that means if it is execute it will execute this path, but the child of last task is already being assigned to this virtual machine. So it will try to schedule the entire path right before the child. So that means we will insert the whole path right before its child that already on this virtual machine, and we will shift forward the child and its successors on that instance. So otherwise, if there's no child of the last task of the path assigned to this machine, and we will need to consider both the pass before the start time of the first task of the instance and also the finish time of the last task of the instance. So the implementation also goes into this way. So firstly, we'll check whether has child on assigned path or not. So basically, we'll check the if the path's last task has child already on this machine. So basically, if the child isn't null, that means there is any child, and we will just insert the path between right before the child and shift the child forward. And if not, we will just regularly check the start time and finish time. If it is fit the requirements, or if it can be fitted of the whole path. So you can see here, assign the whole path to the end. And so let's get back into here. So this is a assign PCP, and also we need to consider if there's no available or applicable virtual machine available. So here we can see if none have been done above, like no existing instance can be found or can be available, we will assign a new instance to this path. So if we go to this method, basically we'll go through all the type of virtual machine and check whether any of virtual machine type can have the can meet all the sub-9 requirements, and as well as deliver the minimum cost. So we will choose that virtual machine type. So let's get back to the method assign PCP, and here is a assign PCP. Yes. So after we assign the PCP, we'll update the task time of the PCP. That means for every task in this PCP partial critical path, we have to update the successor's EST, EFT, and also the predecessor's LFT. So you can see basically it does the same thing. Firstly, it updates the successor of the task. It loops through all the tasks in this PCP and update the successor of each task. So if we are to take a look at the updated successor, we will find the method to update the EST and the EFT. So if we take a look at update the EST, we will see it says the maximum as a negative infinity, and then we will compute the EST for this task. So if it goes into here is a method, we will get the no parents, and to check the no parents, because we will check the parents' actual finish time and then plus the communication time. So basically it's a quite same as we did initially, but with actual finish time instead of the minimum execution time. So this is how they update the EST, and EFT is basically just the EST plus the execution time. So that will be very easy as well, very similar to the successor, to the EST as well. And also we need to update the predecessor. So this is to update the LFT for the tasks, for the predecessor tasks. So you can see it's updating the backward. If we go to the update LFT, we will see it's same. It computes the LFT by the key, and basically it implement a formula to get the parents, to get the children's early start time and minus the transfer time, as well as minus the transfer time. So I think it's strictly aligned with the formula we see from the paper, and also to check the minimum one. So this is how to update the predecessors, and also it will recursively call the assigned parents on the tasks. So if you notice that in the paper, it does the same thing, recursively assign parents, and this is what we did at the beginning to the exit node. And now if we goes into one PCP, and we will still check the available parents on every task, and if there's any, we will recursively call this assign parents. So I think let's go back to here. We've done update task time, and so here we've done assign parents and from the exit node, and then we will initialize a global schedule, because at this moment actually all the schedule has been done, and we will initialize a global schedule, and also we will, based on every virtual machine in the virtual machine pool, we will initialize a local schedule and put all the tasks on each virtual machine and into the same local schedule, and then combine them together. We will get a global schedule that is ready to send to the workflow executor for execution. So I think this is pretty much of this whole class, or this is whole implementation to make it work. So I think that's what I will talk about in this video. Hope you find this is helpful. Until next time, happy coding. Thank you. Have a great day.